apply Ampere's Circuital law in a spiral wire? Ampere's Circuital law. Ampere's Circuital law is useful in finding the magnetic field due to current under certain conditions of symmetry. Ampere's Circuital law states that the line integral of the magnetic field B around any closed path is equal to mu naught times the total current crossing the area bounded by the closed curve. Mathematically, integral in closed loop B dot dl is equal to mu naught times current I in. Suppose we have wires I1, I2, I3 and I4, where cross denotes the inward direction of current and dot denotes the outward direction of current. If we draw an imaginary loop covering current I1 and I2 and assume the direction of imaginary loop anticlockwise, this loop will be known as Ampere's loop. Magnetic field because of all wire on this loop is equal to B net. Then we can write integral in a closed loop B dot dl equal to mu naught times current I in. Note, here B is the net magnetic field due to all wires whether inside or outside on the loop, and I in is the current due to wires inside the loop. Ampere's loop direction gives the direction of current, which is positive. Curl the fingers of right hand in the direction of Ampere's loop, then the direction of thumb will give the direction of positive current. Magnetic field at all points along this loop will be the same and will be tangential to the circle, which is also the direction of the length element dl. Hence, integral in closed loop B dot dl equal to mu naught times current I2 minus I1, where I2 is in the direction of Ampere's loop and I1 is in the opposite direction. As a simple application of this, we can derive the magnetic field due to infinite current carrying wire using Ampere's Circuital law. Draw the circle through P with center O and radius R. Assume the direction of Ampere's loop is in anticlockwise. By using right-hand thumb rule, the direction of positive current comes out to be inward. Angle between magnetic field B and dl element is equal to 0. Thus, the closed integral of B vector dot dl vector is equal to B into integral dl, which is equal to B into 2 pi r. The current crossing the circular area is I. Thus, by Ampere's law, B into 2 pi r is equal to mu naught I. This implies magnetic field is equal to mu naught I divided by 2 pi r. Let's take another example which was asked in JEE Advanced 2011 exam. Question. A long insulated copper wire is closely wound as a spiral of n turns. The spiral has inner radius A and outer radius B. The spiral lies in the xy plane and a steady current I flows through the wire. The Z component of the magnetic field at the center of the spiral is. The options are solution. Let's take a small strip of thickness dx at a distance x from the center of the coil. The number of turns in this strip can be calculated by using unitary method. In coil length equal to b minus a, there are n turns, so in 1 unit length there would be n divided by b minus a turns. Therefore, in a strip of length dx, the number of turns dn would be equal to n divided by b minus a into dx turns. Magnetic field due to this strip element at the center of the coil will be dB equal to mu naught into dn into I divided by 2x. On substituting the value of dn, this expression becomes dB equal to mu naught into n into I divided by b minus a into dx by x. On integrating this expression from limit a to b, we get magnetic field B equal to mu naught into n into I divided by 2 into b minus a whole multiplied by ln b by a. Hence option A is the correct answer.